Well, hello, all of you joining us via the internet. Welcome to the virtual William W. Hay Railroad Engineering Seminar. Before I introduce our speaker, there's a few things I want to tell you about. First of all, to remind listeners that if you want to ask questions, you should use the question box on the side of your screen, and one of the moderators of this seminar will read them to our speaker at the appropriate time. The William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois. And on behalf of all of us, we thank AAR, BNF, CN, Hanson Professional Services, and Union Pacific Railroad for their ongoing support of RailTech. It's greatly appreciated by all of us here on campus, as well as obviously by those of you participating via the internet. I'd also like to extend a welcome to the almost 140 people who are joining us from at least different continents around the world. That's one of the benefits of these virtual seminars. It's a lot easier to get on this as opposed to get into one of our conference rooms here on campus. So we're really glad you can join us. And the list includes representatives from freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, technology developers and suppliers, and others. And again, we're very pleased that you can join us from the various corners of the world for what I'm sure is going to be a fascinating presentation. Those of you who wish to receive PDHs for your participation, please send us an email at heyseminar@illinois.edu with the information as described in the email announcement that you received for this seminar. Also, as a reminder, our next Hay seminar will be in 2 weeks on Friday, December 4th, and it will be given by Dr. David Thurston with the Canadian Pacific Railway, who's going to give us a presentation on CP's engineering challenges crossing the Canadian Rockies. And that'll be our last Hay seminar for this semester, but we'll resume again with the 2021 series early next year. Well, as I'm sure all of you tuning in know, railroads are a critical element of the U.S. freight transportation system. However, despite this vital role, more than half of their bridges in the rail network were built before 1920. That they're still functioning effectively is a testament to the engineers who designed and built them more than a century ago, and the ongoing inspection and maintenance structures by railroads today. However, current inspection practices do not ensure that all the information needed to economically optimize both short and long-term condition assessment is available. Our speaker today will describe research being conducted here at the University of Illinois, developing an autonomous, affordable system for monitoring railroad bridges using wireless smart sensors. By overcoming the challenges of monitoring railroad bridges wirelessly and autonomously, this system is expected to become an essential tool for railroad bridge engineers and decision makers of the future. I'm very pleased to introduce our speaker today, Professor Bill Spencer. He received his PhD in theoretical and applied mechanics here at the University of Illinois in 1985. He then joined the faculty at the University of Notre Dame, where he taught and conducted research for 17 years before returning to Illinois, where he currently holds the Nathan M. and Ann M. Newmark Endowed Chair in Civil Engineering. His research has primarily been in the areas of structural health monitoring, structural control, cyber infrastructure applications, stochastic fatigue, stochastic computational mechanics, and natural hazard mitigation. Professor Spencer is a highly respected researcher and a prolific author with more than 700 papers and reports, including 2 books. His varied accomplishments in civil and structural engineering and his many honors that he has accrued throughout his career are far too numerous to mention today. But his most recent research is on investigation of structural health monitoring systems and smart wireless sensors using advanced computational tools. I'm very pleased to introduce my friend and colleague, Dr. Bill Spencer, who will describe his latest research on autonomous wireless monitoring and assessment of railroad bridges. So, take it away, Bill.
Thank you, Chris. It's a real pleasure to be here today and to tell you about some of our work. My name is up here, I'm giving the presentation, but there are numerous people behind this research, from current students to students that are graduated and are off doing great things on their own. I want to acknowledge their considerable contributions to the work that I'm going to present to you today. This is the overview of the presentation. I'm going to first discuss the background, how we came to this problem. And then in particular, I'm going to discuss the technology background, which refers to the technology of wireless sensors. And then I'm going to discuss the autonomous monitoring framework that we've developed under the sponsorship of the FRA. Cam Stewart is the program manager, as well as through the support of a number of the railroads, in particular, strong support from Sandro Scola at CN. And then we'll talk about data-driven inspection assistant summary. And then we'd like to mention some opportunities for participating in this research. We're looking for partners. So we've all seen pictures like this of the aging civil infrastructure in the United States. This is an older report card from ASCE, but it's certainly one that is still the case today. Numerous bridges, about 1/4 of them are structurally deficient. And this shows that it's not a problem of just a few regions. It's throughout the entire United States that we have this problem with bridge infrastructure. Primarily, this is focusing on highway bridge infrastructure. And the main way that we do inspection to assess the safety of that infrastructure is through visual inspection. And we need to, this visual inspection gives us the opportunity to assess the state of the structure to ensure that it meets the operational demands and is safe to be used. Now, many people think that ASCE is a relatively conservative organization. But this report, this Vision 2025 report, the link is down there if anybody would like to review it. It talks about relying on and leveraging real-time access to living databases, sensors, diagnostic tools, and other advanced technologies to ensure that informed decisions are made. We no longer can expect our infrastructure to perform adequately just by putting it out there and then going and looking at it on an occasional basis. And that leads to the idea of structural health monitoring, putting sensors on your structure, getting that information back, and then converting it into actionable information. Now, the traditional way to do structural health monitoring is with wired sensors. And I show you an example in the lower left. Those are 400 wired strain gauges in a laboratory. And as you can imagine, if someone asks you to tell you where strain gauge number 133 hooked into that mess there, it would be really challenging. And so on the right is just one of numerous examples. This is from work that was done by Celebi and Caicedo. It was led by the University of Buffalo. And so they installed 86 sensors, accelerometers on the Bill Emerson Bridge. This bridge is near Cape Girardeau, Missouri, over the Mississippi River. And the average cost of each sensor channel was about $15,000. And the majority of that was due to the cabling, because you can see some of the distances there, and you'd have to put these cables in conduits, and it would be quite challenging to bring all that data back to some central location where it could finally be sent on to where it could be utilized. And so our work has primarily focused on wireless sensor technology, and this has been an active research area for me since I came back to the University of Illinois in 2002. And the reason is that these wireless sensors, they solve the cost problem. You don't, at least part of it, you don't have to worry about the cabling because they transmit their data wirelessly, but there's so much more that they offer in that context. The intelligence capabilities of the onboard microprocessor. There's a very powerful microprocessor inside of each of the nodes. There's the small size, there's wireless communication, ease of installation. If you can see right here, we install these sensors just by using the use of magnets. And moreover, there's 8 sensing channels in each of those boxes. So you really get a lot of power out of a wireless sensor. And since the early 2000s, or even the late 1990s, researchers at Illinois have been actively developing wireless smart sensors. And this has been a collaboration between Professor Gul Aga's group in computer science and my group in civil engineering. Now, part of what's come out of that, I just wanted to show you some of the things that we've done before I get into the railroad application. This was a 2009 deployment on the Jindo Bridge, which is between the southern tip of the Korean Peninsula and the Jindo Island. This was a trilateral collaboration between the University of Tokyo, Professor Yozo Fujino and Tomonori Nagayama, a PhD graduate from here, and KAIST, Professor Chunbang Yoon, Professor Jungjo Jung. They also have strong connections to Illinois. And then our group at the University of Illinois. We installed 113 wireless sensors in a demonstration project with 669 channels of sensor data. And roughly the average cost of that was $50 a channel. Now, of course, we were using graduate student labor, which is cheaper than normal labor, but still, you can see that the economy is there. And the deployment, we put sensor nodes on the cables. It turns out that the cables are one of the critical elements of a cable-stayed bridge. We put them on the deck nodes, and this is one of my students, Hongyi Zhou, who's now at the University of Arizona. And this is the base station that sent the information back to the University of Illinois, as well as our other partners. And the outcome was that we could get the acceleration data, we could get the wind speed, and we were able to, in real time, determine the tension in the cables, which, as I mentioned, is one of the critical elements of the cable-stayed bridge. We took that information, and in a more recent deployment, this is the Dubai Eye. This is the world's largest Ferris wheel with a diameter of 250 meters. And it's currently under construction. It's been slowed down because of the pandemic, but it has 192 cables, and each of those has our wireless sensors on them so that you can determine the tension in those cables and maintain the safety. So this shows the deployment. We had a base station there, and the outcome is that we're able to get those cable tensions. We measure the accelerations, we extract the natural frequencies, and using algorithms that are embedded in the sensors, we deliver the cable tensions. Now, more to the railroad side of things. We first started monitoring railroad bridges in 2007. This is the Rock Island Arsenal Bridge, built in 1896, and it's a swing bridge, an amazing feat of engineering, the way that this system works. And so we installed our wireless sensors on this bridge. This is Kirill Mechatov. If you guys remember Tim Prunkert is up here helping us with the installation. And we also had some strain sensors that were fiber optic strain sensors installed there. And the outcome, we were able to determine the strains for the events. The most critical events was during a bridge swing where the two halves of the bridge were cantilevered in each direction, and we were able to determine and build models of this structure that we could use for subsequent monitoring. That was with the U.S. Army Corps of Engineers. The first bridge project that we had with the Class 1 railroads, this was with Canadian National, with CN. The Calumet Bridge, which is up near Homewood, near Chicago. And we monitored this CN track 1 and 2. So there's 4 bridges going across there. The first one is the Metro, the Chicago Metrolink, and then the other 2 are railroad bridges. And this 4th one on the right is closed. So we installed our wireless sensors there, strain gauges, wireless strain gauges, wireless accelerometers, and we were able to monitor the train loads. This is a comparison in this first graph at the bottom, a comparison between the manifest and the estimated train loads from measuring the strain on the rail, the shear strain on the rail. And over on the right is the comparison here between the measured data, and let me see if I can get a laser pointer. There we go. So over here on the right is the comparison between the model that we built from the measured responses and the measured data. And that was just at a couple of points on that structure. And we were able to use that to simulate the response of trains going over this bridge and predict the strain behavior of every single element in the bridge. If you look at this right model of the bridge, the 3-dimensional cartoon on the right, what you note is that the elements in the back have more red, signifying compression, than the elements on the front truss. And that's because this was a double-track bridge, and so the bridge was loaded asymmetrically, as is reflected here. My former student, Fernando Moreau, he's now at the University of New Mexico, assistant professor out there. He did a survey with Professor Lefebvre in 2011, survey of railroad engineers. And the #1 topic of research interest in the assessment of bridge performance was measuring displacements under traffic, under live traffic loads, under live train loads. And so that started our efforts to develop a means to determine the health of a bridge based on the displacements of that bridge under live loads, under revenue traffic. And so the basic idea is that the displacement of a bridge, whether it's the lateral or the vertical or the transverse, or longitudinal, excuse me, this is a good measure of the overall performance of the bridge. That is, if you measured your bridge displacements under revenue service traffic this year and you measured it next year, and you get base statistically the same displacements, that's an indication that your bridge hasn't experienced any significant degradation. On the other hand, if this year you find that those displacements, those measured displacements, are significantly different than the previous year, then you might expect that there's something that needs to be looked into further. So this is a series of tests that are shown on the screen today currently, in which we measured the displacements of these bridges using traditional displacement transducers during different stages of here, Bluford, Fulton Phase 1, Freeport, Yazoo, different phases of construction and of repair. And we found that the displacements were indeed correlated directly to the state of the bridge. Now, this is just to show you how we did this measurement. This is on the Bluford line. Sandro Scola, we're very thankful that he helped us do this measurement. And we had to build, CN built scaffolding there. I believe that putting up that scaffolding was on the order of, it was thousands of dollars. And so that's not really an approach that can be replicated easily for every bridge in the inventory. Moreover, we looked at the possibility of using accelerations because accelerations are reference-free measurements. They don't require that you have a reference up there. You don't have to build scaffolding. And so what we found is that that's a really hard problem. The blue is the exact result that was measured by the displacement transducer. And the red is what's done, what's achieved by just doing double integration of the accelerations. And so what we are focusing on is over on the left is a signature. This is the total displacement of the bridge. And I think this is important to illustrate what we're doing. And on the right is the dynamic displacement, and below is the pseudostatic displacement. So this would be what's happening under basically the static train weight, and this is how much it wiggles. And so what we've been working on is the dynamic displacement as an indicator of the health of the bridge. That is the wiggling. How much, if it wiggles more today than yesterday, that's probably not a good thing. One has to account for environmental effects, but we'll talk more about that shortly. So we developed a reference-free estimate of bridge displacements, dynamic bridge displacements, where the idea is that one would deploy the wireless sensors, use this reference-free displacement estimation method for the dynamic displacements, and then have a database to compare to assess whether those displacements are within the realm of reason statistically, or whether they fall outside of what would be expected. And so then that's that green, yellow, red guidelines, and then focus in this project, which was supported by the FRA, we focused more on bridges of higher interest, which were timber trestle bridges and pin-connected steel truss bridges. And the goal of all of this effort, and I'll show you where we are today, is to produce an inexpensive, effective, quickly deployable, and smart tool to assist in estimating railroad bridge condition. Okay, well, let me tell you a little bit more about the technology background of wireless sensors. Wireless sensors have been researched since the late 1990s. A lot of this work started at UC Berkeley, at Stanford. It was picked up by Intel Research Labs. This iMote was the Intel mote. And a lot of our work was built on this iMote 2, a lot of the early work. And as you might imagine, Intel Research Labs did work on this. That was what we had used on the Jindo Bridge deployment and the government Arsenal Bridge deployment. But it went out of, they decided not to make a business out of it, and so it went out of production. And we were in a situation where we needed to look around and try to find some of these other manufacturers, whether they had a product that would meet our needs. We were not in the business of making our own wireless sensors. However, we found that many of those products were not designed with the engineer in mind. They were designed to do fancy stuff, but they didn't really have the high fidelity sensing capabilities, the ability to open source platforms so that you can put your own algorithms on there, et cetera, et cetera. And so we decided, we embarked on a path to develop our own wireless sensor node. We call it the X node. And a couple of the key features is that it has a 24-bit analog to digital converter. That's a state of the art. It gives you very, very precise high fidelity measurements. It's fully autonomous. We've made it solar powered, and we have cellular connections back to the base station or back to the cloud. So we have the ability to provide near real-time remote data retrieval and reporting. And this platform is very robust. We've been working with it for several years now. And I always joke that if it can survive in the tremendous heat of Dubai, then we're in pretty good shape. So the wireless sensor approach is that we measure the displacements. We then do a time convolution integral, and this is what we call the filter. And if anybody is interested, we have several papers on this topic. This is not confidential information. Anything I tell you about today, we have papers to to support the data and the results. And then we obtain the dynamic displacement directly from the sensor node. Now you might ask, well, how do we know it's correct? And so this is a pin-connected steel truss in Freeport, and unfortunately, the trains only went over this bridge at night. And so we developed a method to use cameras to be able to track the displacement of that bridge, and we put our wireless sensor node on there, and we compared the acceleration base, the reference tree estimates with the camera nodes. And here, I don't know if you guys can see that, but these are live videos. And the reason I show you this is just to indicate that although the human eye can see very little of what's going on here, these computer vision algorithms are quite effective, and they can determine the displacements directly from these video images. And here is a comparison of the difference between the vision-based approach in blue and the reference-free acceleration-based approaches in the orangish-red color. And what you see over on the right is an inset. It's this little section here. But we had an RMS tracking error of about 1.6%. And so we view this as being a good validation of the approach that we were taking for this accelerometer-based displacement estimates. Well, how do we build that into a framework that can be used by railroads? In general, if you might imagine, if you put your wireless sensor out there on a bridge, and then you wanted to measure all the time so that you could be ready when those trains come over, because they come over at random times, then you're very quickly going to deplete the battery of the wireless sensor. And so what we did was we developed a train detection sensor, or a trigger sensor, a wake-up sensor. And it's very, very low power. You can run about 8 years with this sensor on a button battery. And we built that into each of our wireless nodes. Moreover, those wireless nodes are able to sense the accelerations before the train gets there, a second or so before the train gets there, through this trigger sensor. And then the main node wakes up with the high-performance accelerometers, 3 channels, X, Y, and Z, measures the data, and then in the end, it's all melded together. So you have a complete picture from before the train got on the bridge until the train gets off. And then that sensor goes back to sleep. We have then real-time onboard displacement estimation. We have 4G cellular technology that the nodes talk to and then can ship that data back to the cloud server. And then there's cloud-based management. So the nodes can either only upload the data to the servers, or it can also send text messages because of the cellular technology to alert the stakeholders as to issues that may need their attention. So this is an overview of the idea from sensor to actionable information. Many of the sensors that are out there, they provide data. And data is not directly of use to the railroads. You need information, actionable information. And so the idea is that we have however many sensors on the bridge. We do synchronized sensing so that we know what the traces, how the traces correlate with each other. We adjust for the orientation because they may not be, this is done automatically because they may not be installed exactly in the X, Y, and Z direction. And then we do this dynamic displacement estimation. And then we have a database management system. And this would be the data that one collected for that particular situation. And so you can say, well, gee, if today my measurements were in this region, that's within the statistical error bounds that I'm willing to accept. But what about these points out here? What should I do with them? And then once you have that information, you can make a rapid, preliminary, or alert assessment. And so this system, you might imagine that there's really three modes of operation. One could do it on a particular bridge, and you could say, well, this bridge last year had these displacements, and this year it had the current displacements. And so you have a historical perspective on the displacements of that bridge under revenue service traffic. Another mode of operation is that you compare the displacements of this bridge to other bridges in the inventory, which are of a similar class. So you wouldn't compare a pin-connected steel truss to a timber trestle bridge, but you might imagine that you could compare the displacements of timber trestles to timber trestles. And then finally, there's the opportunity. Usually there are multiple bridges on a particular line. What I'll show you in a little bit is some data that we collected from a number of timber trestle bridges on the Buford line. And so you can compare the bridge to bridge at a given point in time displacements, the data. Now, our goal is to produce what we call a sensor in a box. This is a concept that I think is well suited to the COVID-19 era that we're in. And the idea is that there's no extra installation steps. You turn it on, you use the magnets to attach it to the structure, and then it works. So you've got ultra low power consumption. It can stay in a sleep mode for more than 2 years, assuming that no trains go over, but that's not the case. And so we have this solar panels that can be used to ensure long-term operation. We have intelligent reconstruction of the various data streams that can be collected and put together. Low delay data retrieval. So within a couple of minutes, you can have the data from the current train and decisions can be made. And then this idea of edge computing and cloud edge computing means that you're doing the computing at the sensor node combined with cloud computing. It really harnesses the rapid assessment ability. And this is a picture of our interactive web interface that we've put up. And so this is sponsored by the FRA, but Embedded Technologies, Canadian National Railroad, G&W Railroad, they've been helping us out by letting us monitor their bridges. And here is an example of some of the near-time real data that you could access. Here's the milepost, the owner, the node ID, humidity, weather, what's the primary data ID? Do we have latitude, longitude? Here is the acceleration that is measured, and here is the displacement that's calculated. We also have a secure authentication there because it's your data. It's not the world's data, and so one could set up their own data server, but we're setting this up so that it can be used for people to have a test drive, so to speak. And then one has that real-time condition reporting, and then the raw process data can be exported should you have an interest in seeing what was actually collected. And we've put it up in an Excel spreadsheet. You can download that. Here you can see the different dates and times that in each tab that the measurements were taken, and so that's all directly available. Now, what I'd like to do is just show you some examples of what we've done. And the first is for 2 campaign-style deployments that were 1 year apart. This was on CN's line, the Buford line, and the Bluford subdivision in Illinois. Again, Sandro Scola and the entire team at CN were just tremendous. I want to just talk to you a little bit about what we did here. We mounted these sensor nodes. This is the wireless, the cellular connection. These are just regular wireless nodes. So this is the one that can communicate to the cloud. And what we did was we put a steel plate onto the caps, the timber caps, using deck screws. We just took down 4-inch deck screws and an electric screwdriver, and we mounted that up there. And then there are two magnets, one here and one here, that attach the wireless sensor to the bridge. Similarly, for these solar panels, the idea is that you can, the first time it takes a little longer to deploy the sensors because you have to put the plates up, but subsequently you just go up to the site and then place the sensor in place. If it's an area where you're going to have extreme weather, you might put a little silicone around the magnet so you don't get water freezing underneath it. But these magnets are such that we've never lost a node to date. Here are the various installations that we did. And it's on the order of 5 to 10 minutes per sensor. The thing that takes the longest time is putting the ladder in place to get up there, or however it's going to be installed. And this is what we found is that the structural behavior is highly correlated with operational and environmental conditions. And so these are the maximum lateral displacements versus the days of deployment. This was a deployment for 2 months. And what you can see on the bottom is the temperature. And so this red line corresponds to freezing. When the temperature dropped below freezing, the displacements were reduced considerably. And you can imagine that if the ground is harder than the bridge piers, they don't move as much under the loads of the trains. And so we used a Gaussian regression process to standardize the measurements with respect to the various factors to eliminate this environmental impact, and then statistical process control for automatic change detection. So the process is that you get the acceleration measurements, you estimate the dynamic displacements, you then compare that to expected behavior, you add that monitoring data or you make a decision, and then you can add that monitoring data to your database, and then you can assess the condition. And the idea is that you have this green region, yellow region, and red region. And what we've done here is that we don't. If you just get one spike that's larger than what you expected, that may be a wheel flat or some other kind of issue. So we've looked at the situation where you have to get consecutive measurements that are out of bounds before you send an alert. This is where we had 3,200 data sets from this deployment, 260 distinct trains, and these were the different bridges. This is the days of the deployment. And what you can see is that it's very easy to be able to determine the difference between a freight train and the Amtrak train, because we can get the speed of the train directly out of the measurements. And this shows some of the data, and this is what this is how many times we had data points that were outside of the bounds. And so most bridges showed little difference. The nodes, you had 1 or 2, but these 2 nodes on this bridge consistently showed that they were not the same as a year before when we had monitored that bridge. And so this also shows the maximum lateral displacement from 2019 to 18 to 19. And what you see is that we have a lot higher low frequency, or in 2019, we have a lot more high amplitude displacements than we did in 2018. So it's a statistical process, but you had a shift to the right for those 2 data points. Just want to show you one more example. This was with the support of G&W, and so they were extremely supportive. This is the pin-connected steel truss. It was short-term monitoring. We actually monitored 3 bridge spans. This was a 2-span over the White River. And what you see here is this is the maximum displacement, quite small dynamic displacements. And the left and the right span, as shown here, are consistent. That is, we don't have a higher span, a higher displacement on the left span than on the right span, as indicated by the black and the red lines. And then we didn't have enough sensors to put them on both sides of that span here. So in span 2, we have that this truss is consistent with the truss above. So the west side and the left side of the span 1 are given consistent behavior. And that was confirmed by the October 2018 inspection, which showed that really there was no section loss for this bridge. This is bridge number 2, short-term monitoring effort. And what you see here in this bridge, we monitored it, is that the west and the east side show considerably different displacements. So it's about 4 times larger on the west side than it is on the east side of this bridge, of those truss elements. And that was consistent with the inspection report of 2018, which showed that the truss on the west side had multiple members with section loss, as indicated in this figure to the right, while the east side had no section loss. And so that would be one explanation. It shows that this type of an approach can identify problems in the bridge. So this is the future outlook for where we're going from here, is that we want to get a baseline framework which is fully autonomous. No humans in the loop are required, other than to have the experts' input regarding the results. So we want you're going to need to look at the data. The analogy that I make these days is that if you've ever had an MRI or a CT scan, the amount of data that is generated is tremendous. And so computer algorithms will look at that data first, and it'll highlight regions that the radiologist should examine more carefully to make an assessment of whether that's normal or not. And it's the same type of thing here in terms of what we're expecting. So the initial target structures for monitoring are ones that would have known structural concerns and are scheduled for maintenance or replacement. That's what we're looking for, so that we can demonstrate the potential of this approach. As I mentioned previously, the inspection results are incorporated into the monitoring system and database for recalibration of future monitoring campaigns. And so in conclusion, what I hope to have shown you in this brief presentation is that we've been working hard to develop a fully autonomous tool for assisting railroad inspections under in-service loads, and that we've developed that and validated it with full-scale deployments. That this provides an inexpensive and quickly deployable means of obtaining bridge displacements under those in-service train loads. And this smart sensor technology has been used to overcome limitations of existing wired and other wireless monitoring systems. So we're working currently on additional capabilities to meet the needs of the railroad industry based on our interactions with the various stakeholders. And for example, one of those is to use this node to develop a strategy for effective bridge impact detection. Now, we're seeking industry partners to conduct additional field testing and validation, that is, beta testers, to learn what you're interested in, learn what problems you have, and how we can make this, this research that we're doing better. So the opportunity is to instrument and monitor structures of interest to the railroads, to you out there, and in particular seeking deployments on bridges with known or suspected structural issues. And the good news is, thanks to the FRA support, we have resources to loan our beta testers, our industry partners, systems that can be provided at no cost. So they're on long-term loan for you to see if, to help us in developing this research into more effective tools for the railroads. Again, I want to acknowledge the people at the FRA, Cam Stewart, Sandro Scola and his team, Bill Reel and Jeff Herbach at G&W. We've been talking to other short line people, and then in Better Technologies, they're the ones that are currently developing these wireless sensors. So with that, this is my contact information. I'm glad to take any questions that you might have at this point, but in the future, feel free to contact me. And in particular, I hope there are some takers for the beta testers.
Well, thank you very much, Bill. As I expected, an outstanding seminar, very interesting and informative. And we do indeed have some questions. Can you hear me all right?
I can hear you. I turned off my camera because I didn't like looking at myself. And so I'm trying to figure out how to turn that back on. I mean, my camera's on, but I can't see you anymore. So.
Oh, well, I'm not showing myself.
So, oh, that's okay. You're so handsome, Chris. I mean, you should let us see you.
Yeah. Okay. So the first question is, and this is kind of a theoretical question. You may recall, I'm sure you recall, the failure of the I-35 bridge in Minneapolis in August 2007. Yes. And the questioner would like to know, how might this technology have mitigated that event?
So I'm not sure that this technology could have mitigated that event. That event was caused by a design flaw in the gussets and almost unimaginable situation where you had traffic on a huge amount of cars on both lanes of that bridge, and so that was an anomaly. And so what? So I don't want to claim that we could have done something there. It may have been possible, but that was a very local phenomenon, and I don't think we could have done much there.
Okay. Next question. Do you have a paper that explains how the dynamic displacement is calculated from acceleration?
Yes, we do. And what I think might be the best, I don't know if you folks have a repository, or you could just put links on the website. I'll send you 2 or 3 papers. We have one paper that's specifically about the algorithms, and then we just published a paper here recently in Bridge Engineering, which is on this system that I presented today, this autonomous framework, and it gives a lot more details than what I presented in today's discussion.
Okay, thank you. And I can also put you in touch with the individual who asked that question if you want to, correspond with him directly.
Sure.
Here's another question. How often do you come across statistical outliers in the displacement data, and how do you handle those?
The statistics that we have is for a relatively small number of bridges, and we're not, so when we find these statistical outliers for these particular bridges, we've reported them back to the railroads, and then it's in their hands what they'd like to do from there.
Okay. Well, the next question is, have you had problems with extreme weather or vandalism with the wireless sensors on bridges?
Yeah, that's a good question. So the extreme weather problems we've been able to handle. You can do that. You can deal with that in one of 2 ways. It's all a question of being able to keep your battery powered. So we use a very relatively small solar panel on there. And if you got cloudy days consistently, no sunshine for 3 weeks on a heavily trafficked railroad, you might have that sensor go dead for a short while. But the good news is that when the sun comes back out, the sensor will automatically come back alive, and it will reconfigure and start sending data again. Now, should one want to, you've got a critical situation where you want to avoid that, you can either put a larger solar panel on there, or you can provide some sort of a bigger battery, or you could provide direct power. So it's all about appropriately managing the power budget for these wireless nodes.
Okay. Yeah, we've had several questions also related to whether you've had a vandalism problem.
Oh yeah, we haven't. And I think that's because we haven't done any bridges in town. I mean, these sensors on the Blueford line, they were kind of, those bridges are out in the country and they're up pretty high. So you'd have had to have been a pretty interested individual to be able to get up there and mess with them. But certainly we've talked about that. I mean, as you can see on my slide here, we got that nice cover on it, and it's actually got a clear spot in it where you can see lights blinking and everything inside and know that it's working. And we've talked about if we wanted to put this in a more frequented area, that we're going to have to use camouflage or something. That's an ongoing thing. And we may have a new project to instrument the Green Street overpass. It's a bridge in Champaign. It's a steel girder bridge. And if we do that bridge, we're going to have to take serious consideration of how we're going to protect against vandalism. I guess you could always put high voltage signs and things on there, but then some people just try it anyway, find out that you're just joking, and then you lost your sensor.
There's another question related to the power requirements, I think. They're asking, what kind of train headway was associated with your 8-year battery life?
I'm not sure what was meant by the headway, but
I think how many trains per hour or whatever.
Yeah, that's actually that's not so what this trigger accelerometer is it's a very, very low power accelerometer. It's not high fidelity. It's made so like when you get a certain level train, it'll be able to measure it. So it's a 16-bit ADC, but it's got a maximum sampling rate of 100 hertz. It doesn't have really high precision acceleration measurements, but it can run continuously. Doesn't matter how many trains go over the bridge, it can run continuously for 8 years on a button battery. But it's just for waking up the node. The real power has to be is in the X node for the high precision, high fidelity measurements.
All right. A lot of interest in the batteries and the power. So can you speak to how many
words? It's a 10,000 milliamp hour or a 10 amp hour lithium polymer battery. It's a single cell, 3.7 volts. So we can use some very efficient technology there. And so the node, if you did run it continuously, it would go for, like I said, a couple weeks, but we want to stretch that out and manage that power budget. So that's I hope that caught most of the questions, but if not, please continue, Chris.
Well, the other one's related to cost. This questioner is asking $50. He thinks you said $50 per sensor. Does that include fixed cost or is that only variable costs?
So that was for the old wireless sensor, and there was a lot of that's basically a different beast. What we have now and it's no longer available. That was the research prototype out of Intel Labs, the IMO 2. What we have now is this X node, and it has the 8 channels of 24-bit ADC in each of the boxes, and including the solar panel, the magnets to put it on, the data storage, the sensors. 3 of the channels are this accelerometer, a general purpose accelerometer, and that's about $1,000. And so if you take $1,000 divided by 8, that's on the order of $100 per channel. That's for the hardware costs, and then the installation would typically be done by the railroads themselves.
Okay. The next questioner is wondering if this system could be used to monitor conditions of post-tensioned precast concrete segmental box girders.
So this system, as I said, of the 8 channels of data acquisition that are in the little box, 3 of them are dedicated to this accelerometer, but there's 5 other channels that can be hooked up to any high-level voltage source. And so if you have a displacement transducer or a strain gauge or whatever, that can be hooked up to the sensor and measured directly. So I don't have a sense of exactly what they're interested in measuring, but I'd be glad to speak with them in more detail after the seminar.
Okay. Next question. And you kind of already spoke to this a little bit, but they were commenting that what we saw were rural bridges. Were any in urban settings?
So we haven't, I mean, we put sensors on bridges that are in more of an urban setting, but I think that our partners at the railroads have deliberately chosen bridges that are not in an urban setting because the deployments are easier. We don't have to stop traffic or anything to do these deployments, and their efforts were in-kind contributions. And so should we have to, in the near future, we're looking for this bridge impact monitoring at some urban bridges. And so I'll have maybe more to tell you next year in a subsequent HAY seminar.
Okay. And the follow-on question from this individual is, if you were in an urban setting with tall buildings, do you anticipate any communications problems? They also suggest there could be solar power problems if you have a lot of tall buildings. What are your thoughts on that?
That indeed is a problem. And so on that Jindo Bridge deployment that I showed you, the one in Korea, we put the sensors on the bottom of the bridge, but we then had to move the solar panels out on the side of the bridge so that we could get adequate sun. And so it depends on the particular deployment of how you're going to do this, and each of them are going to be slightly different. But with the buildings, what you typically do is you just put your cellular node, which also can measure responses, but you put your cellular node that's relatively near your other nodes that are collecting data, and then the cellular node should have good connections with your cellular network in a city, and so there should be enough towers to compensate for those buildings.
Okay. Well, questions keep coming in, but right now we have 5 more, if you're okay to hang in there for a few more minutes.
No problem.
Obviously lots of interest, so that's a good thing. Do you have any sense of when this product might be generally available to monitor most bridges, or do you think that this technology will primarily be used for special cases?
Our goal is to have it so that it can monitor most bridges. And the best laid plans, the software has bugs in it. And so that's why we're seeking these beta testers to help us to figure out where the bugs are. But nominally, it's ready. I mean, it's ready to be deployed. And we just need to make sure that it truly meets the needs as the railroads see it, not meets the needs as we see it.
Okay. Another questioner, how often do you come across faulty sensors and have some kind of self-checking system that guards against malfunctioning units that will reduce false alarms?
Good question. Yes, indeed, we do. The sensors report back with a health check on a regular basis, and if they're missed at any particular time, then that's noted, and then decisions can be made accordingly. In the early versions of our sensor nodes, we indeed did have, it wasn't that unusual to have some, 10% or so of your nodes go dead after some period of time. But we've worked hard to refine and harden the system, and now we find that the failure of the nodes is really quite a rare event.
Okay. Next question is relating back to the one earlier about the statistical outliers. How do you say you refer these back to the railroads, but how do the railroads, interpret this or answer this? And, would they come to you for advice on that?
They're the experts. And so far we have reported this to for CN and for G&W, and they said they're going to go have a look. I'm not sure whether they've had time, because that was just before COVID-19. I'm not sure if they've had a chance to go have a look, but we haven't gotten any feedback just yet.
Okay. Next question is a fatigue and fracture type question. Have you taken the displacement histories and used them to compute stress spectra at fatigue critical locations for fatigue analyses or fatigue crack growth analyses?
We did that when Fernando Moreau was in Illinois for the Calumet Bridge at up near Homewood. That was a funny story in that when Sandro told us we could monitor this bridge, he said it's a relatively new bridge. You're not going to find anything wrong with this. And I said, oh, really? When was it built? And he said, oh, in the 70s. At least for most people, something that's a 50-year-old bridge would not be considered new. But we looked at fatigue studies on that bridge, as I showed you in that one cartoon. We could use the model that we had to get the strains in all the members, and we looked at what the associated stresses in critical regions were, but we didn't find any problems. But that's a problem that we're very much interested in.
Okay. Next question. What type of cellular, I think they're referring to communications, are used?
So as you may know, each network has their own cellular modems. And in your mobile phone, you'll have multiple modems built in. Currently, we're using the one that is on the AT&T network. And we're going to develop, CN is interested in Verizon, that's what they use. So we're going to develop a modem that will work on the Verizon network. And we're sticking primarily, we're sticking to 4G technology. We're not jumping into 5G. So we've got LTE communication, but we're going to stay away from 5G until that standard has settled down.
Okay.
I'll mention
just
one thing further is that we've had some interest in developing a satellite connection for bridges that are truly in remote locations. And of course, it's a trade-off between the cost and the data throughput. But that's something that we're interested in exploring at some point in the future. That was some folks up in the northern parts of Canada interested in that.
Okay. We've got two more questions, and I think we'll wrap it up. Next one is, do you think this technology is going to remove the need for drones to supplement manual inspections?
No, I don't believe so. I mean, the drones give you different information. We're also using drones for railroad and building inspections, particularly in the post-earthquake era. So for post-earthquake rapid assessments. And so that gives you a different kind of information. And I think it's all very beneficial and can serve different purposes.
Right.
Maybe we'll do a talk on that at some point in the future.
Sounds great. All right, the last question is, how much data, approximately how much data does each train pass generate for, say, a 200-foot bridge, or for each 200 foot of bridge?
So I mentioned early on that I wanted to acknowledge my students and their hard work on this project, and I'm not sure I can tell you that. If you forward me who asked that question, I'll get them a real answer, but the best I could do now would be a seat of the pants calculation, and I wouldn't want to put wrong information out there.
Maybe we could settle on a lot.
You know what? It's not like the video data. The video data, you can generate gigabytes of data,
right,
in a few minutes, and this is in the megabyte range. So it's not, we've got a 4 gigabyte SD card in there in each of the nodes. And you can store, so what it does is each train that comes over gets stored on that card. And then that way, if something happens, you've got a lightning storm and a lot of rain or something, and the cellular connection is too poor to transmit it back, it's still there. When the weather passes, you can retrieve that data. And you can put, I'll just say, a train load of data on that SD card. And so it's not so much, whereas with video, you fill up one of those SD cards pretty much in the blink of an eye.
Okay. Well, that's it for the questions. Let me just conclude by, again, thanking you very, very much, Bill, for a fantastic seminar. I knew it would be, and completely fulfilled our expectations. And obviously the more than well over 100 people who participated today, I'm sure they appreciate this as well. And again, obviously the volume of questions is indicative of the interest. So thanks very much. And we'll conclude now, and I'll just give you my very best wishes for a wonderful weekend and a happy Thanksgiving.
And the same to you, Chris, and everybody out there. I appreciate your attention today, and I hope that it leads to future collaborations. So thank you very much.
All right. Thanks very much. Bye-bye.
Bye-bye.